Hi, folks. I'm Vanessa Sockett. I'm a computer scientist at Lawrence Livermore National Laboratory. And today we're going to be talking about compatibility for HPC, a story of rainbows and schedulers. So let's start with something fun. Some of you have probably seen this on the internet. The premise here is that you have a man on the right that is putting shapes into holes, and he says, okay, where does the cube go? And the girl on the other side is unusually excited about this. And she says, yes, the square hole. And he puts it in the square hole and she goes, yes. And she's really excited. So this progresses and he gets some more interesting shapes. Okay, where does the cylinder go? And she says, the circle. And then he says, no, the square hole. And you see her face go from confusion to extreme levels of distress. And guess what, folks? This is a really relevant metaphor because this is how we might see HPC applications. We build them kind of generically when it comes to containers, and we pull them down to our snowflake systems. And the question becomes, is that compatible? Like, is him putting all of these shapes in the wrong hole? Is that really compatible? Well, let's talk about that today. So what does it mean to be compatible? Compatibility is the degree to which an application can successfully run on a host environment, accounting for the variables that you'd expect: architecture, operating system, software, hardware. Now, I say application, and I mean a binary or a container image. And these are sort of the core features, but you'll probably note that many other features could be possible. Now, note what I did not say. I did not say effectively run on a host environment. And so that's going to be something else that we'll talk about. So what does it mean to be compatible? It means that it works. No seg faults, ABI issues, no anguish. Well, maybe a little anguish, but so what is compatibility metadata? Compatibility metadata is the minimum information to ensure that our thing works. Oh, and this is very kind of different than something that's optimized, meaning that it doesn't just work, it works to the best of its little ability, it works performantly. So you can imagine, well, there's going to be a dimension here, but I want to make the point that compatible is not equal to optimized. A lot of people think of compatibility and they think, I want it to run the best. Hold on, folks. Compatible is a question about, does it work? Optimized is a question about, how well does it work? And between that, there is a dimension. So on this side of the dimension where there's sort of a golden color, this is an area where it's not guaranteed to run. You hit some point, some minimum level of compatibility that is the minimum amount of maybe compatibility metadata that you need to ensure that it actually runs. And then you add maybe a little bit more so that it doesn't just run, it runs optimally. So why is compatibility important to talk about right now? Why not last year? The reason comes from container technologies. Not surprising, I love container technologies. So there is a thing called OCI, the Open Container Initiative. The definition is there. We are an open governance structure to basically create standards around how you use containers. So this includes bunches of industry companies. It also includes us in HPC because guess what? We use containers too. And generally the questions that OCIs are concerned with is, how do I interact with a container registry? When I'm pulling a container, what's going on? How do I describe a container image? What is actually happening when I run? We have to have these standards because if we didn't, we would disagree and the ecosystem would just be a total mess. So the reason the time is now is because we started a compatibility working group. It is super fun. And the main question that we're interested in for this working group is, how do I know if my container image is compatible with my host? Simple, maybe not. So where is compatibility relevant in HPC? Let me tell you a couple ways. The first comes down to image selection. So when you're pulling a container, or when you're just pulling one from a SPAC binary cache, you need to choose the one that's going to work for your system. The same is true for building. It's a slightly different context, though, where you're choosing a build environment to actually create that application in the first place. And then scheduling. So if we kind of add in a more automated aspect to both of these things, you kind of want your scheduler to make informed decisions about where to place work based on where it's going to be compatible. Now, let's talk about image selection first. For this talk, we're going to go through these things. We're going to talk about some experiments. How have we traditionally pulled containers to HPC systems? I think you know the answer. We pull poorly. I'm just kidding. I mean, actually, maybe I'm not just kidding. So image selection in kind of the registry world, so for example, Docker pull, but actually it could also be Podman pull, comes down to choosing the first matching platform. So let's say that I Podman pull my awesome container. It hits a registry. Hello, Mr. Registry. Do you have a matching platform in the registries? Let me look at my manifest list. Let me go down the list in the order that they're there. The first one that I have is PowerPC. Nope, that's not going to work. Second one, AMD64, that matches your host. This one's good. Here's your container. Have a nice day. And it's really that simple. But as we know at HPC, platform is not enough. Along with just kind of the diversity of architectures, there's so many other things that we care about. Compilers, MPI, like it is not represented in that extremely simple way that we pull our containers. So what is the working group working on? We're actually doing two things. The first are adding additional core features to that manifest list. So for example, here you see that there's features in that list that could be used to inform the selection. The second is something that we have more handles on, because you can imagine that this list is only going to be like the core stuff that people agree on across industry. MPI is probably not going to make it in there. But for the second part, we're thinking of adding basically an artifact. So the idea of an artifact is it's like a blob that lives in a registry that isn't an image layer. So how might that look? Well, you're still going to Docker pull or Podman, whatever, and you're going to get your image manifest list. Then you select based on platform. Maybe there'll be some other features in there to get an image manifest. And then, okay, so this is what the URL looks like for an image manifest. There is an API called the refers API that if you just change manifest to refers, you actually get a different manifest list, but it's of artifacts instead of manifests. So that's really cool. So use the refers API, and then you get your artifacts. There might be some software bills of materials in there, some kind of compatibility specs, who knows? And here's the thing though, so not all registries actually support this API. So some of them actually fall back to making a tag. So the only difference in the last entry here is that the colon has changed to a dash. And that is actually a tag of the digest. This is extremely hacky, but it's a fallback so that all registries can theoretically support this. Okay, so we have our manifest list of artifacts. We then get our actual artifacts. So the artifact has a manifest itself, and this is actually needed just because if it doesn't, it will be garbage collected. Don't forget your manifest, folks. And so then finally, after like all these layers of things, we get to our actual image artifact that is just like, here's the compatibilities for your container. So, okay, that's a lot. What I'm going to recommend, and this is what I've been doing for my experiments, is to fall back to ORAS, OCI registry as storage. So in this setup, you still start with your image manifest list, but then you get an image manifest and there's actually a URI as an annotation. And that URI takes you directly to the artifact manifest list with different profiles for your application, and then you directly get the artifact. A smaller number of calls here, maybe better, maybe not. And I also want to point out that this doesn't necessarily have to be a container. You could have some kind of binary cache that just keeps a record, again, of where this manifest list lives. Alrighty, so the future of image selection, we imagine a future of more informed pulling. But what about building? So how have we traditionally built and run applications? Well, we have built them where we intend to run it. We log into our special nodes and we build and we run and we call it a day. And of course, this comes at the cost of portability. You're not going to move it to another machine and expect that it's going to work. Why would you do that? And then all of the expertise for how to run it is in your head. So when you go then to the command line, so this is a Flux command, for example, you say, okay, I want these resources, and I want that MPI variant, and I want this resource mapping or topology because I know how to best run my application. And here's the thing about this manual specification, though, there's many details that might actually improve how our application runs that we just like don't have the brain bandwidth to specify. As an example, I/O. Here is a montage workflow run on Pegasus that was optimized with I/O awareness. So for each of these number of nodes blocks, we see the first one is the parallel file system. Then we add a hierarchical cache. Then we add the same cache, but with an algorithm to optimize I/O. And I want to point out for that last case, when we had intelligence there, we saw speedups of about 1.7 to 1.8 times. Time is money, folks. So this is like a big deal. We should be asking for this more, but we largely aren't. So the answer to this question, how have we traditionally built things? Well, manually, and this has really limited a lot of things and probably made things more expensive too. Alrighty, so little man here is asking, well, I don't see what the problem is relying on me. Well, little man, when you go away, all of the knowledge for how to run your special binaries is totally lost. And that's a risk. And also, it's also the case that we can just, even if we built it, we can forget how to run it. Like the next year you come back and you find this binary and you're like, I don't remember how to run this. I don't remember what's in it. So we think that in this case as well, automated approaches that take into account compatibility can better inform. And guess what? The universe is changing. Well, it's not the universe. The build landscape is changing so that we don't just build one application anymore. We build a bunch of different variants. So it's not just a question of like, do I remember how to run this one thing? It's like, oh, wait a minute, I need to choose one out of these 6 first. It's a much larger problem than it was before. Oh, no. That's an understatement. But the great thing here is that we still have build environments. We still have CI and with build systems, with host environment, and it seems fairly easy that we can build our application, but then save all that information in compatibility artifacts. Push them to a registry, don't push them to a registry, we can save it somewhere, it doesn't matter. Now, let's talk about where schedulers come into play, because hopefully they can help us with some of the automation and assigning work to where they're going to be built or run. What does scheduling with compatibility metadata look like? Well, you start out and you're like, hello, workload manager, here's my special workflow step. Can you give me a node? And then your scheduler is like, I see you have this application and you're making this request. Let me check the possible variants that I know about and see if I can satisfy that and compare that with my resource graph. So it looks, and it's like, it looks like it is possible. And I do have a GPU in my resource graph. Here is your node. Thank you. Have a nice day. Sincerely, the resource manager. Great. So we do think that was a very simple, stupid use case, but we do think that automated retrieval of compatibility artifacts can effectively match an application needs to the resources. So we've talked about these 3 things very abstractly high level. How do we test these ideas? Well, we put on our scientist hair like this. And of course, we run some experiments. Warning, these are intended for prototyping. These are not publication ready. My role, I don't know if other people work like this, but I like to make what is something that is very close to production software to run experiments, because then when something's cool and actually works, it's a very small distance to go to actually make it a thing. So experiment number 1 with image selection. We want to demonstrate the added value of compatibility metadata for this use case. So our question, is our application more likely to run, so the compatibility aspect, or optimally run when we add metadata about it? So we start with a matrix of LAMPS builds across all different kinds of architecture, operating system, Rocky and Ubuntu, versions, MPI, GPU or not. Folks, if you need lamps, I'm like a lamps dealer. I got your lamps covered. So I created a tool. Next, we want to generate these compatibility artifacts. I created a tool called CompSpec that basically has these extractors that know how to get metadata about lots of things you might be interested in. So you basically run this for each container image. You get out this artifact. This was the version or the variant that we had at the time that has all of the compatibility metadata we're going to use for the experiment. Push them to registry. I actually did push this to registry. So the top one is the artifact with CompSpec, and the bottom one is the matching image. And then for the design, on a cluster of nodes for each compatibility level, where compatibility level is one of these compatibility features we talked about, we are randomly going to select a host environment. So that's the operating system, the version for a node, which is a pod, because by the way, we are running in Kubernetes. I love Kubernetes. And then we're going to choose a match based on that compatibility level. So here's explicitly the levels that we use. And so base is actually no compatibility metadata. And then we move up through operating system, GPU, and NPI. Then we're going to run lamps. So we're actually going to run lamps and see what happens and see the different outcomes. Alrighty, and then we're going to ask 2 questions. Did it run? How well did it run? And the results, the great thing about presenting is that you don't have to actually wait to run the things, you just have results. Okay, so we're looking at LAMP's reasons for failure across compatibility levels. So this is basically base, no compatibility metadata. This would be just sort of doing it randomly. We see that most of the errors come down to OS ABI issues. That's because sometimes we get Rocky, sometimes we get Ubuntu. By the way, there is an ABI issue between Ubuntu 20.04 and 22.04. I was very surprised here to see that we had even any successes. That number seemed very high to me. Alrighty, when we add in information about the operating system, so we ask for Rocky or Ubuntu, the OS API issues go down a lot, but not to zero because again, Ubuntu still has some issues within it. And we actually start to see MPI errors only because we made it further than we did before. Let's add an OS version. Now those OS API issues go away. The successes are going up. We're still having GPU. And interestingly, when I added in information about the GPU, I think this served as a filter that selected correctly for the other things, where I just didn't have that many LAMP spaces to choose from. So this was when everything worked. Yay. Okay, so compatibility minimum achieved. We found the minimum level for LAMPs to run, but this was a will it run story. Is there a performance story here? The answer is maybe. So when we look at LAMP's wall times, we saw pretty big range. So this is like a tiny, really tiny problem for LAMPs. And we saw a range between 7 and 11 seconds. And it was like, what's going on here? When I looked more closely at MPI, we found the culprit. It was Intel MPI just taking really slowly for some reason. So the compatibility metadata about the MPI variant would be the one that would help you to optimize your performance. And you would basically not run Intel. And I won't tell you which cloud this is on because they actually recommend running Intel MPI, which is kind of strange. So MPI variant is where we kind of went into that threshold of running optimally. So yes, there's a performance story. And for this experiment one with image selection, we learned that compatibility metadata can inform image selection to ensure that our application LAMPs runs. And then we can actually add one more thing so that it runs optimally. But let's increase the difficulty level a bit, shall we? Let's see if we can add compatibility metadata to improve build outcomes with a scheduler. Put those two cases like together, right? Okay, so this is another really fun, exciting project. I decided I wanted to make my own meta scheduler. So the Rainbow scheduler is exactly that. It is a meta scheduler. Itself, in terms of design, it's written in Go, uses gRPC. The main kind of server that you see here is very simple. It has clusters off a very kind of rudimentary jobs queue where the jobs are only there temporarily before they get assigned to the clusters. The cool part of Rainbow is the distributed graph database, where I've so far implemented an in-memory depth first search algorithm. We'll talk about that. So what does this mean? So if you're a cluster, let's say I'm cluster A, I will first need to register to Rainbow, be like, hello, Rainbow, here are my nodes. So I'm going to be giving Rainbow my cluster resource graph. What does that mean? It's JGF, JSON graph format. This has nodes. This is what you're looking at here. It also has edges. If you've ever done anything with graphs in like Python or whatever, you're familiar with like defining nodes and edges. So you give this to Rainbow. That ultimately goes into this cluster resource graph. And then Rainbow's like, yeah, I know about a lot of clusters. And this is actually really cool because these do not have to be real clusters. So I have used Rainbow to simulate 100 to actually a couple thousand actual, fake clusters, and it's really quite fun. So then you need to tell Rainbow about what resources each cluster has. We call these subsystems. So example subsystems are what you'd expect: I/O, storage, networking, GPU, but again, it can be anything. Ice cream flavors, you can have fun with it. But at this point, Rainbow's like, great, I got me my clusters, I got me my resources. You gonna submit some jobs to me now? Yes, Rainbow, patience. So we're gonna take a job, what's called a job spec, a job specification, which basically says like, here's the work that I want to run, and here's the resources that I need at this particular level, like a node. So we submit the job spec, and this is also why gRPC is really cool, because you can make a lot of different clients very easily. And the first thing we go to this cluster resource graph and we say, can this work be satisfied? So what does that actually mean? Well, we do a depth first search to traverse into a cluster. So the cluster has racks, the racks has nodes. And when we hit a level where the person was like, I need this kind of storage for my nodes, that is where we actually look at to see if there's edges to a subsystem graph. So in this case, we're looking for shared memory. Maybe we find it and we say, great, we have our shared memory. I also want to point out, this is where the match algorithm operates. So you may be checking for an exact value, a minimum value, a range. You may actually be traversing that other graph. Anything you can think of it as an interface and go, actually, as is the cluster resource graph itself. These are all interfaces, which means that you can plug and play them, swap them out for different ones, which is important for research because like we change our mind a lot, right? Alrighty, so at that point, we're either going to return because it's depth first search and we found a match, or we're going to return 0. So we might return a count of 1 to be like, yes, I found a slot, or return 0, I didn't find anything. And by the way, you can also traverse deeper into the graph if you so please. So at the end of the match algorithm step, we have best case scenario, we have some clusters that match. Worst case scenario, Rainbow's like, sorry, man, can't do it, not going to happen. But at this point, we give those clusters to the selection algorithm, and we are then going to select the best cluster based on an algorithm that usually considers cluster state and the needs of the job. Now, I have very smart people in my team that are working on these algorithms, and I am not going to talk about that. My simple algorithms that I did were for the default, I did randomly. And then I did an additional constraint on memory for a reason I will tell you shortly. And so the question is, how does the compatibility metadata get into here? Well, what I can do is I can dynamically add it to the job spec at different levels. Then it can populate and inform the match algorithm. It can also inform the selection algorithm. Okay, so for experiment goals, we wanted to run a simulation, or I guess I wanted to run a simulation that demonstrates how compatibility metadata provided to a scheduler can add value to the scheduling process where value is reflected in successful builds and maybe improve runtimes and thus costs. No promise there. So where did I go? I went to talk to the SPAC team and I was like, hey, SPAC, do you build things every once in a while? And they're like, yeah, Vanessa, we build lots of things. And so they gave me a database of over 422,000 SPAC builds across 1,089 packages. I filtered this down pretty heavily because I wanted packages with successful builds with greater than or equal to 100 actual builds. And so we have rich metadata that ranges from the VM to aspects of the VM. And importantly, we have build duration. And I was really excited about this. The reason is because when I started doing exploratory data analysis and building models from the data, I found that I could build really good models that would predict build time. And when I used regularized linear regression, and for example, I used an alpha parameter that would set a lot of the coefficients to 0 to basically perform a kind of feature selection. The coefficients that wound up not being 0, meaning they were kind of the strongest, they were always consistently memory. So what that tells us is that memory can kind of be used as a proxy for performance, because when you give a build more memory, it gets faster. And so if there's some kind of cost, well, that could go down. But this is like the classic trade-off, for example, like with something like a GPU. You could pay a lot of more money to get a GPU, and your stuff is going to be faster, but it's a balance. And there's going to be some level where you don't want to do that. Okay, so for this design, I simulated 100 clusters. They were named after colors of the rainbow. It was just totally fantastic, based on a random choice from these actual build environments. I then registered subsystems for each. So again, those metadata that matched to what I had in the SPAC data set. And then for each of my final set of over 30,000, I was running this on my computer. And side note, I also had no power during that weekend, so I was running it on my computer and my car. So 30,000 was plenty. For each compatibility dimension, so those are basically the subsystems, we are going to submit the job spec to Rainbow to be scheduled for the cluster. Now, I am going to run Rainbow in a sort of developer mode that's actually going to give me back all the selected clusters so I can see how many matches that I have. Then I'm going to perform the selection, and I'm going to do that either randomly or I'm going to do something with memory. And then I'm going to calculate scores in plots that I'm about to show you. Okay, more results. Here we go. So first, we're looking at the trade-off between build success and cluster matches, starting with adding no compatibility metadata. So you can see that there's like very, very low build success, and every is like, that's great. No, it's really, really not. So this next set of points, I'm testing single subsystems a la carte. Welcome to the restaurant of subsystems. We have subsystems a la carte. So for minimum memory, didn't really add that much. Same with compiler version. Compiler name, same. I guess the number, interesting thing about version is it's going to severely limit the number of matches you get, but it's not really going to improve build outcomes. But at least compiler name gives you more matches, but they're both terrible. We don't care. Architecture, finally one that makes it jump up. And this makes sense about at the 50% level. This means about half of them will randomly land on the right one, and then but the build success isn't great because there's still other attributes that are needed. Now we get into the multiple subsystems. So this was me adding more compatibility metadata to that job spec. When we hit architecture and compiler name, this is finally when build success was like a little bit under 80%. And only when we hit architecture and compiler version did it really shoot up to 100%. And we've unlocked the minimum level of compatibility achieved. It's architecture and compiler version. And I'll quickly show you the same plot. I won't go through it, but it has the same kind of logic as before. For example, looking at architecture, we don't have any failures because we had a wrong architecture. Exactly. Great. So we hit 100% successful builds. Is there a performance story here? Can we go back to that algorithm that I made, where basically I want to choose the optimal memory for the build to minimize the cost? The answer was no. Okay, so the minimum cost, what you're looking at here is additional cost per job. And this is over the ideal build time. So the best real world build time that this package got in the SPAC data set. And we actually see the minimum cost is at that first level. Now, why could this be the case? The case is because I totally came up with these cost per node hours fairly arbitrarily, but you can see that when you get to the kind of the highest levels of memory, it's quite a bit more expensive. And so that tells us that, the expense probably wasn't worth it. We're also dealing with state data, the fact that clusters will fill up and then you won't be able to schedule to them anymore. But the lesson that we learned is that when you're trying to optimize for costs, it is really hard and it's really fragile, especially given changing costs. If I had done different numbers, this would have been a different outcome. Alrighty, so what did we learn today? The need for compatibility metadata is upon us. And so we are coming up with these specs in the OCI compatibility working group. They will soon be out there, and communities are sort of called to action to start thinking about the compatibility metadata and the artifacts that they want to produce for their apps, for their images, whatever. This includes you, the HPC community. The next thing is that it's really cool to run experiments like this. So the Rainbow Meta Scheduler is empowering us to develop and test different algorithms, run experiments. So I encourage you to do similar. Rainbow's open source. Please come and give feedback, try it out, contribute. We can have a lot of fun. And then finally, we have this higher need to work together. And it's very hard. It's one thing to work within HPC, right? But it's much harder to work between HPC and cloud. And actually, I would say that a lot of the issues we've had with container technologies from way back have been because we have not had our voice at the table. So we need to show up, we need to work together to solve a lot of these problems with respect to compatibility. It'll run things better, save money. I don't know how to give the right argument for this, but I know it's important. Alrighty, so that's all I have. Thank you for listening to this talk. I hope that you have a wonderful rest of the conference, and that if you look up in the sky, you may see a rainbow scheduler.